everyone. We are going to continue talking about the work kinetic energy theorem. So we want to see how that works out with some examples. We'll do one with just symbols, and then we'll also do one with some numbers so we can see both. And then we're going to go into, hopefully, gravitational potential energy. So let's start off with our example here. The last thing we talked about in class today was that the work kinetic energy theorem just means, or just states, that when work is done on a system and the only change in the system is in the speed, then that means the net work done on the system has to equal the change in kinetic energy. So that's where we got our work equals delta K. So I know that for work kinetic energy theorem, my work done on a system is going to be equivalent or equal to that change in the kinetic energy of that system. Okay. So let's look at this problem for our first example. We have a 6 kilogram block initially at rest is pulled to the right along a frictionless horizontal surface by a constant horizontal force, and that force has a magnitude of 12 newtons. Yep. Find the block's speed after it has moved through a horizontal distance of 3 meters. Okay, so the first thing, I just want to write everything out. So let's just write out all of our variables first. Okay, so we know on this problem, they gave us a mass, which was 6 kilograms. They gave us a force, and that was 12 newtons. They gave us a displacement, so we knew our delta R vector was 3 meters. What else did they give us? I think that's it. Oh, we know also, initially, so the initial speed was 0. And ultimately, the question is saying, find the block speed after it was moved these 3 meters. So that means I'm trying to solve for VF. Okay, well today we said that work was equal to, according to our work kinetic energy theorem, work is equal to our change in kinetic energy. Well, that change in kinetic energy is just equal to the final kinetic energy minus the initial, which is also equal to, so 1/2 mv squared, if I'm thinking about final, minus 1/2 the initial velocity squared. Well, we just said that our initial velocity was 0, so if this is 0, that whole thing now becomes 0. So really the work is equal to 1/2 mv final squared. Well, we don't know the final, and we do know mass, but they didn't give us work. They did, though, tell us that the work, or the force that was being applied was constant. Will you answer that, please? The force that was being applied was constant, so we know that we could find work by a constant force by taking the force times our displacement vector times cosine theta. Okay, well, my angle here is really non-existent, so I know that my cosine theta would just be 0. I was given a force, that's 12 newtons, and I was given a displacement, which was 3 meters. So then I know that the work that was done had to have been 36 joules. So let's just plug in our numbers here. So work was 36 joules, and I have, that's equal to 1/2 times the mass, which was 6. So we'll say times 6 kilograms. And then I'm trying to find that final velocity, or final speed, I should say. So I have that VF squared still. Okay, so if I want VF, I'm going to take then the square root 6 joules, and actually that times 2 over 6 kilograms. So if I do that, we should get a final speed of 3.5 meters per second. Okay, so ultimately on this one, we just had to apply our work kinetic energy theorem, and we know that work is equal to that change in kinetic energy. So we know that's final minus initial, which is 1/2 mv final speed squared minus 1/2 mv initial speed squared. Well, our initial speed was 0, so it's like that thing just completely came out of our equation. So work was just equal to 1/2 mv or m final speed squared. I didn't know work though, but they told us in the problem that we had a constant force and we knew its displacement, so we could find the work that was done. So we did that right here, and we got the work to be 36 joules. So I just plugged that in for work. I had the mass, so I could find that final speed. Okay, let's look at the next one. Okay, on this problem we have a man wishes to load a refrigerator onto a truck using a ramp at an angle shown. He claims that less work would be required to load the truck if the length of the ramp were increased. We have to determine, is his claim valid? So usually when they're asking us to find if the claim is valid, then they want us to show using some type of symbols. So he's saying, so he claims that less work would be required to load the truck if the length of the ramp were increased. So if I'm increasing the length of that ramp, I'm going to do less work. So let's show this. Okay, so on this problem, let's imagine that also, let's add to this problem actually, that for this problem to also work, then the refrigerator has to be moving on a frictionless surface, and let's say that it's also moving at constant speed. So let's add into here at constant speed, and we're assuming that there's no friction. And actually, let's just draw this here. So here was H. Here's my displacement. My ramp. There's theta. This would be the length of that ramp. And then I have my guy. Oh man, this is going to be terrible, guys. I apologize. Pushing some refrigerator. That's just, yeah. That's a great picture. Okay. So it's just a guy pushing a refrigerator up the ramp, and he's trying to get it into the bed of that truck. I have to show if his claim is valid, that somehow the work done is going to be dependent, what he thinks, on the length of this ramp. So he's saying, or asking, is work dependent on the length of the ramp? Okay, if it is, then he may be right in his claim that if the length of the ramp were increased, then he would feel like he would be doing less work. If we find that it's independent of it, then he's just going to be wrong. Okay, so we know that if this is at constant speed, if speed's not changing, then delta K has to be equal to 0, right? If the speed's not changing, if it stays constant, then my K final minus my K initial would just be 0. So that means ultimately that net work that I'm thinking about would also be 0 because of the kinetic energy work theorem, or work kinetic energy theorem, because work is equal to that change in kinetic energy. Okay. Let's think about the forces, though, that are acting on that refrigerator, because we have to think about that refrigerator as our system here. If I think about all of the forces that are acting on the refrigerator, actually, let's think about the work that's being done on the refrigerator. So I have some amount of work done on the refrigerator by the man. So the man is doing some amount of work on the refrigerator. So let's say that the net work, we'll just call this W net. So my net work is equal to the work done, we'll just say, by the man. But then we're also going to have some amount of work done by gravity as well. So I'm going to have work done by the man, and then I also want to find or think about the work done by gravity. Okay. Well, we just said that because the delta K is 0, then our net work has to be 0. So 0 equals work by the man plus work by gravity. So work by the man, say by man, is equal to a negative work by gravity. Okay, well we also know that work is equal to a force times some type of displacement. Well, since he's moving it in a vertical direction, I need to think about, since he's trying to lift it up into or roll it up into the truck, he's moving it really over some height here. So I know that, let's look at the work done by gravity, because if we think about work as being a force times a displacement, I know that the force of gravity is just m times g. So I could say that here is equal to a negative mg, and then I still have that displacement vector here, so delta r. But I don't want delta r, let's say it in terms of what we have here in our problem. So the displacement, because he's thinking that the work is dependent of the length of the ramp. So the displacement would be my length of the ramp times cosine theta, but that refrigerator is also at a 90-degree angle already. So that refrigerator is already at 90 degrees here. So then if I'm also adding here then that theta, so it would be, my delta R would be L cosine theta plus 90, whatever this theta is here. Well, if we're using our trig identities, the cosine theta plus 90 is also equal to a negative sine theta. So instead of this delta R, I could write mg L cosine theta plus 90, and all this was negative. But L cosine theta plus 90 is equal to a negative sine theta, and that's just from trig identities. Then I could say, instead of a negative L cosine theta plus 90, I could say mg L sine theta, because cosine theta plus 90 was just a negative sine theta. So we could do mgl sine theta. Is there another thing, though, that we can write for mg sine theta? Let's get that part out of here. Okay. There's another thing, though, we can write for this L sine theta. I know that height and length and theta are also all related to one another, because I could say that height over, so my opposite over my hypotenuse is equal to sine theta. So I could say that h equals L times sine theta. So instead of L sine theta, work by the man is actually mg h. So technically speaking, is our question, is work dependent on the length of the ramp? We can show here, no, it's not. Really the only thing that is going to the only thing that we'll really need for work or to take into account is the mass of whatever we have here, our acceleration, so our force in the displacement in which it's moving. So ultimately we're starting here and we've moved it up a specific height. So the length of the ramp doesn't even matter in terms of the work, because this is the displacement ultimately that it's going to be going. So we can prove that his claim is wrong just by knowing some trig identities and by applying that work kinetic energy theorem as well. Okay, so I'm going to stop here. We'll start off with the gravitational potential energy tomorrow in class, but actually we'll start off with questions that you have for these two things at the beginning of class, okay? So if you have any questions, write them down, bring them to class tomorrow, and we will talk. Have a great night, guys. Bye.